Good day, everyone. We will now go back to the formula for ultimate moment, which is equal to the reduction factor phi times the nominal moment. And in our first video, the nominal moment is always equal to the tensile force multiplied by D minus the depth of compression block A over 2. Or it is also equal to the compressive force, capital letter C, times the quantity, the effective depth minus the depth of compression block A over 2. Now, how do we solve for the reduction factor phi? If you already know the aqueous strain sub S. Strain sub S is the aqueous strain. So, we need this figure. If this is the strain column and this is the reduction factor phi column, you notice that if the strain is 0.005 and up or higher, the value of phi is always equal to 0.9. And if the strain, computed strain is 0.002 or lower, the phi value there would be already 0.65. But if it is in between 0.005 and 0.002, which is called the transition part, then if your strain is between these two, then the phi can be computed as follows. You notice that if the value of strain is 0.005 and higher, we call that as a K-square tension controls. But if the strain is 0.002 or lower, then that is the K-square compression controls. And in between these two is the transition part. So to be able to solve the phi in this transition part, we need to do the following. So this we do first 0.005 minus 0.002, which is this one, and 0.9 minus 0.65 on this part. Then the aqueous strain minus 0.002 here. So the same is true on the other side, phi minus 0.65. So we have now this equation. Okay. Then from here, we get the difference between these two, 0.005 and 0.002, so you get 0.003. The difference here is 0.25. The denominator, we rewrite also the denominator here, and we now cross multiply. So 0.003 times phi minus 0.65 here is equal to 0.25 times the denominator there, aqueous strain minus 0.002. Then we will now solve for the phi here. So phi is now equal to, so we will rewrite this 0.25 times the strain actual minus 0.002 divided by 0.003. Then we transpose the 0.65 there, so negative, so it becomes now positive 0.65. Then we just change the position. So we will now solve the value of phi is now equal to, we will write this first, 0.65, plus this term here. So, but we will write first this. This term here is strain actual strain minus 0.002, and this is there. But we should multiply this by 1,000, so it becomes 250, and we multiply this also by 1,000, so it becomes 3. This is now the common formula of determining the value of the moment reduction factor in most books and reviewers. But we still have another way of deriving another formula for the moment reduction factor, which will be shown next. So this is another way of determining another formula for the moment reduction factor phi. So we will now change this to this one. And we'll do it that way. So first, 0.005 minus 0.002 over 0.005 minus the strain, actual strain computed is equal to, so the larger bracket, so we have 0.9 minus 0.65, smaller, 0.9 minus P, over 0.9 minus P. Then we will get the difference first, so 0.003 over the same denominator minus strain in the speed is equal to 0.25 over 0.9 minus P. Then we will cross multiply, so we will get now 0.003 times 0.9 minus P is equal to 0.25. So we cross multiply that 0.25 times 0.005 minus the actual strain in the speed. Then we will compute for phi here. So we will now divide all these terms by 0.003. So if you divide both sides by 0.003, then what remains on the left side is this, 0.9 minus P is equal to 0.25 divided by 0.003 times 0.005 minus the actual strain in the speed. So we will transpose this negative phi so that it will become positive. So there it is. So what remains on the left side is 0.9. We transpose this on the left side, so it becomes negative 0.25 over 0.003 times the quantity, 0.005 minus the strain in the speed. Then solving for phi and writing this on the right side, the formula becomes now 0.09 minus. We multiply 0.25 by 1,000, so it becomes 250. We multiply this also by 1,000, so it becomes 3 times the quantity, 0.005 minus the strain in the speed. So this is the other formula in computing for the phi. In our next topic, which is investigation problems, what we can usually solve there is the actual strain in the steel, the strain soon test. And if the actual strain in the steel that you will solve is 0.005 and above, then the value of phi in this formula will be automatically 0.9. But if the value of the actual strain is 0.002 and below, and we call that compression controls, then the value of phi would be 0.65. And if the value of the actual steel strain is between these two, then you need to compute already the value of phi. And we can use these formulas. Take note, I told you earlier that this formula is the most common formula found in books and reviewers. And you can never see this formula which was derived earlier. So we will now use these two formulas if in the investigation problem the actual steel strain is found to be 0.0035. So in the first formula, we will now substitute the actual strain here to be 0.0035, this one. And if you're going to solve the phi, you'll get now 0.775. Using the other derived formula, phi is 0.9 minus 0.005 minus the actual steel strain times 250 over 3. We will now substitute the known actual strain in the steel of 0.0035. And if you're going to use the same formula 2, then you'll get the same value as that found in the first formula. So now you don't have any problem now in determining the moment reduction factor. So we shall now take an investigation problem, which is a rectangular beam with a width of 300 millimeters and effective depth of 500 millimeters. The properties of concrete and steel. then this is always the modulus of elasticity of steel, 200,000 megapascals. You are required to determine the depth of compression block for a balance condition. Second is the balanced steel area. And the last to be solved is the moment capacity for maximum steel area in a balanced condition. So, before you can solve this correctly, you should be able to draw this as your guide in your solution. So, this is the given cross-section. The base is 300. The effective depth up to the center of the steel is 500 mm. So, in the strain diagram, up to this part is the C. The distance of the neutral axis from the top fiber under compression. And if the depth is 500, then this is 500 minus small letters. In the strain diagram, this is the permissible strain in the concrete, 0.003. And for a balanced condition, this will be automatic. The strain at yield point is always equal to Fy over the modulus of elasticity of steel. And if you will solve this, it will be 414 over 200,000. You will get exactly 0.002, 23 decimal places. Okay? So this is now the value of the strain sub 1. So 0.002. Then, solving for the value of C, since you already know this and that, and you are given the effective depth, so you can already solve the distance of the neutral axis from the top fiber under compressions. So, from similarity of triangles, 0.003 is to C, as to 0.002 is to 500 minus C. So just consider these two triangles. Solving for C, you will get now 300 millimeters. Then you can now make use of the formula. The depth of compression block is equal to beta times C. To be able to determine the value of beta, our F prime C is 28, so our beta is 0.85 times the computed value of C, 300. The depth of compression block now is 255 millimeters. That is now our answer for requirement A. So this is now our answer for requirement A. So to be able to answer the balanced steel area, we make use of the diagrams for a balanced section. So from here, C is equal to T, summation forces horizontal. But our C compressive force is equal to 0.85 F prime C times A times B is equal to the area for area of steel for balanced condition, A sub SB times Fy. Since we are making use of this, the strain sub y is equal to Fy over the modulus of elasticity of steel. Then it means to say that our figure is in a balanced condition. So using that, substituting all values, F prime C is given. Our A is already known. Where is it? This one. Our base is 300. Our Fy is 414. So we can already compute the area of steel in balanced condition. So this is now your answer in requirement. Let's go to the last requirement. What is the moment capacity for maximum steel area in a balanced condition? So we still make use of the same figure. So ultimate moment is always equal to phi times, this is the tensile force in balanced condition. So this is now ASB. Then times Fy times the quantity D minus A over. So what is the value of phi? Phi can be determined by knowing the value of the strain. Because the strain is 0.002, therefore the fee that we will use here is immediately 0.65. Our AS here is this one computed, the AS at balance condition. FY is already given for 1/4. The effective debt is 500. And our computed A in the balance condition is 255. Substituting all this, the ultimate moment capacity is now equal to 279.368 kilonewtons per kilonewton. So this is now the answer for our requirement C. So that is all about the solution of our problem. This is a steel set reinforced concrete beam with in a balanced condition.